Hi guys, I'm Li-Sheng Liu and I'm really glad and honored to be here to present my thesis presentation to all of you guys. And my topic is about augmented reality surgical navigation system integrating with deep learning and automatic scanning. So let's get started. So because in our cases, it's all about how to support and assist surgeon to conduct the EVD surgery. So what we will do is to let AI and artificial intelligence and augmented reality to work harmoniously. So because we want to let AI to after training and deep learning to learn where is the target point that we want and then select it automatically and then send the position of the target point to the AR part of our system, which is probably more front end of this system. And then with several auxiliary functions that can assist surgeon to conduct the EVD surgery. So let's start with the AI contributions in my thesis. So in AI contribution here, that we chose and selected UNet as our neural networks, and then we also select and chose the dice loss as our final loss function. And also we implement the cross validation because that we are lacking of the training set of the total amount of training set because we only got uh, totally 10 set of DICOM from the patients so that we need to do the cross validations at the end. And then after training, we add the post-processing into the UNet to increase the accuracy and the true positive rate. After that, we will find the target on the indicated slice of DICOM. After that, then we will send the index of the position to the AR project to the AI project so that the AI project could visualize all the functions to the surgeons and to assist the surgeon to conduct a UVD surgery. Alright, so uh, let's talk about the post-processing after training. So post-processing in our cases is to remove the small connector regions of the predicted ROIs, which is region of interest. And basically, uh, uh, it just eliminate the fuzzy part around the contour and to lead to the better accuracy and the true positive rate. Right. So as you can see here, that we got a lot of fuzzy part around the contour. After the post processing, will be cleared. Right. So let's talk about the contour comparison. So as you can see here, around the ventricle, the red contour, which is the label contour, and the green contour is the predicted contour generated by UNet, by our system. And we calculated and we calculated accuracy pixel by pixel, and the final accuracy is 99.98%, which is pretty good. And talking about the indication of target point. So the basic concept of it is search the area that contains the biggest amount of ones, which is the white part of this diagram, slice by slice. And then after that we will indicate the number of target slice because for instance in the axis maybe we got 256 numbers of we totally got 256 in 256 icons in x-axis, but we want to indicate the specific slice of the DICOM, and we want to know which what number of the DICOM, what number of the slices is that. So we want to indicate the number of the target slice, And then we will draw the cross on specific slice and then seal the position of target to CSV files so that the AI project could obtain the position of the target from CSV file. Right, so this is the improvement by far. So as you can see, because in the beginning we chose categorical loss, but after that we found that dice loss is more suitable in this case. And after the post-processing, after adding the post-processing, we could see the accuracy, true positive rate, F1 score, and J-card similarity. All of them are increased, and the false positive rate is decreased. And comparing the papers from 2017 to 2021, our proposed thesis got the best results. And before 2017, because there are no relating papers in terms of AI hydrocephalus detection implementing in any cases, so we didn't found it. So I just select the period among this. Right. So let's talk about the AI contributions in my thesis. So the abstract is consisting of automatic virtual image scanning and several auxiliary functions, including DICOM slice real-time display and the generation of surgical trajectory and the color-based angle calibration and attribute. So start with the automatic virtual image scanning, and I would call it instant and fast scanning because as long as the camera point at the image target of head, it will start to scan. And why I call it fast, because it just took 4 seconds to finish all the registration, and it's also the 3D virtual scanning as well. And talking about the DICOM slices real-time display. It will because after the training we will receive after the AI parts we will receive the index of target position from AI, right? And then we also got the options of manually select the target by surgeon. And among all of those trial, the average accuracy is 1 millimeters with the deviation of 0.1. So this is the before the selection of the target, and this is after the selection of target. So after selecting the target, we want to select the entry point as well. After that, we will have the trajectory between the target point and entry point. And then we will have the extension of the trajectory, and the different color means different type of things. So red trajectory here means that the entry point and the edge point of the navigation stick is not overlapped with each other, and the angle is not correct as well. And the yellow trajectory, which means that the edge of the navigation stick and the entry point are overlapped, but the angle was wrong. And the green trajectory here means that both position and the rotation or the angle of this trajectory is correct, and it's all set to conduct the surgery. Alright, so this is pretty much about my thesis, and thanks for the attention. Thank you.